Hello everyone, how are you? I hope you all are well. In this lecture, I will show an algorithm about linear list search problem. This is a problem of online algorithm. In online algorithm, we don't know the inputs from the future, rather than we only know the inputs of the past and the present. So we have to um, take some decision on what we got from the past input and the present input. So, what is linear search problem? So, given a set of items, let me take the laser point. Given a set of items in a list, you can think it as a linked list or something like that, where the cost of accessing an item is proportional to its distance from the head of the list. That means it is a linked list and a request sequence of accesses. The problem is to come up with a strategy of reordering the list so that the total cost of accesses is minimized. So let me visualize it. Suppose that we have a head like this, and the value of the head is 5 or something like this. Okay, so this is 5, and this is the pointer. Another element, let's say this is 3. Another element, let's say this is 2. Okay, and so on. This is, let's say, 10. Okay, so here are 4 elements. If we give an index to each of them, this is, let's say, I'm using one best index. This is index 1, this is index 2, index 3, and index 4. Okay, so if you want to search for 10, you will have to move 10 step, right? 1, 2, 3, 4. Sorry, 4 step. To access this element, to access 10, you have to jump 4 steps. So the cost of accessing it is 4. On the other hand, according to this arrangement, if you want to access 3, this is 3, and it will cost 2 units. Okay. So this is the problem. Will we will get some input instance. For example, suppose that we want to find 10. Then we want to find, let's say, 5, we want to find 2, we want to find 3. Okay. So suppose that after get querying about 10, if we get our list like this, 5, 3, 2, 10, our list is looks like this. And we are accessing 5, and 5 will cost just only 1 unit, right? So this is constant time. So after accessing 5, if our algorithm, if our list looks like this, then accessing 2 will need just 1 unit of time, okay? Because 2 is in front of the list. After accessing 2, if our list looks like this, 3, 2, 5, 10, then querying with of 3 will cost just 1 unit of time because 3 is in the beginning. So this is the optimal solution, but we don't know how to work with the optimal solution or how to get the optimal solution. Rather than firstly we want to develop some easy algorithm. So this is our first easy algorithm. What is it? Our input is some sequence list. Okay, initial list is 1 to n in natural numbers. And the sequence of request is I1, I2. For example, I1 is a query about 7, I2 is query about, let's say, 3, and so forth, so on. We want to search item ij, if it exists or not, okay? And we want to minimize the total cost because you know that the cost of query is the length of that particular element from the head, okay? Distance from head. So strategy is move the access item forward. But how many positions should I move it to the forward? We don't know. For example, look at here. If we want to access 10, let me create another list. Let's say 1, 2, 3, 4, 5. Okay. So for example, you are querying 3, and if you want to move at the beginning, it will look like this: 3, 1, 2, 4, 5. Then for example, you are querying let's say 2, then it will look like this: 2, 3, 1, 4, and 5. If we move it to the forward, but we want to move this with 2 items or 3 items move forward, then what should we do? We want to see this. The algorithm one is tells us to move the accessed item forward by 2 position. For example, our list is 1 to n. This is our list, and we are requesting n, the last position, the last element, the biggest element of the linked list. So what will be the cost? Look at here: 1, 2, 3, and n minus 4, n minus 3, n minus 2, n minus 1, and n. We are moving the last item forward by 2 position. We are moving n by 2 position. Okay, so moving n right here: n minus 3, n minus sorry, 1, 2, yes, n minus 2, and n minus 1. After accessing n, the linked list will look like this. So but we are requesting n times. So in the first request, the cost will be n because n is at a distance of n from the very beginning of the linked list. In the second iteration here, this n, let me use another color. This n is n minus 2 position. Distance of this element is n minus 2 position from the beginning of the linked list. So this cost will take n minus 2, and this will take cn square. Okay, but in the previous slide we knew that the optimal solution will take n plus 1 plus 1 plus 1 cost, because in the first iteration the last item is at the last position, and to access it we need it will cost n. It will cost n. From the second iteration to the nth iteration, it will cost 1. Look at here. Look at here. So let's say after accessing 10, our linked list looks like this, and after accessing 5 costs a constant amount of time, or 1 unit of time, because 5 is at the first position. So optimal solution will give n plus 1 plus 1. That means n plus n minus 1, because this is the first iteration. And this is next n minus 1 iteration. In each iteration it will take 1 unit of time. That's why in n minus 1 iteration it will take n minus 1 unit of time. So this is 2n minus 1, which is less than 2n. So the competitive ratio is our algorithm divided by optimal algorithm. Our algorithm is cn square. On the other hand, optimal algorithm is 2n. If we eliminate n from denominator and numerator, we will get cn over 2. And here it is, we get cn over 2. If n tends to infinity, then our competitive ratio, CR means competitive ratio, the competitive ratio will tend to infinity. So this is not a good algorithm to solve this problem. So that's it for today. I hope you understand this lecture. I'll see you in some other day. Till then, take care and study hard. Okay. So bye bye everyone.